In this video, we're going to consider the following question. If I have a linear time invariant system, and let us say that I know the impulse response of this system. Based on just knowing the impulse response of the system, can we say if the system is memoryless, causal, stable, and invertible? Okay. If we can, how can we find out if the system is memoryless, causal, stable, and invertible? Now, before I go ahead with the lecture, I want to recall the fact that for a linear time invariant system, the impulse response of the system suffices to characterize the system entirely. So it seems natural that by just knowing the impulse response of the system, we should be able to say something more about the system or some other properties of the system as well. Right? So this is what we are going to look at in this lecture. So let's first see how we can determine if a system is memoryless or if a linear time invariant system is memoryless. The main idea here is to look at the convolution sum or the convolution integral. Now we know that for a linear time invariant system, the output of the system y of n is related to the input of the system through the convolution sum. But we also know that the convolution sum is commutative, which means I can write the convolution sum as summation h of k times x of n minus k. And writing it in the second way is going to make it a little bit easier for us to determine when a system is going to be memoryless. Okay. Now if we look at this summation here, what the summation tells us is that the output y of n can be formed by taking some linear combination of x of n minus k's. Okay. But we also know that if a system were to be memoryless, then y of n should depend on the input, namely x of n, or you can say should depend only on the value of the input at the same time. Well, what that means is that y of n cannot depend on x of n minus k for any non-zero value of k. Okay. So now we want to see what property this h of k has to have such that the summation does not depend on x of n minus k for any non-zero value of k. And that is kind of easy to see, because what this tells us then is that h of k has to be 0 for all non-zero values of k. Right? Only in this case will this summation not contain terms of the form x of n minus k for non-zero values of k. Okay, so that is then that then tells us how we can determine if a linear time invariant system is memoryless by just observing the impulse response. So the final result is that if h of k is 0 for all k not equal to 0, or equivalently h of n is 0 for all n not equal to 0, then the system is memoryless. What this also means is that h of n is pretty much a delta function, except that it's a scaled delta function. It can take any arbitrary value at time 0, but for all other values of this k is different from this k, so let's just call this something else. Let's call this as some constant c. So h of n, the impulse response needs to be of this form. Only in this case is the linear time invariant system memoryless. In the continuous time case, the same argument can be used with the convolution integral to show that h of t has to be some constant times the delta function. Only in this case is the system memoryless. Okay. So to have a quick example, here is a linear time invariant system, and let us say that h of n is given here. Is this system memoryless? Well, the answer is no, because h of n is non-zero for two values of n, 0 and 1. So it's clearly non-zero. I'm sorry, it's clearly not memoryless. And we can also see this by explicitly writing a relationship between the output and the input for this particular h of n. And you can see that the output y of n will be given by 2 times x of n plus x of n minus 1. And we have this term here which indicates that the system has memory. Okay. Now let's move on to the next property, namely causality. Or when can we say that a linear time invariant system is causal? Or what property should h of n possess for this to be causal? And the idea is going to be very similar to what we did in the case of determining whether the system was memoryless or not. And we'll begin by looking at the convolution sum again. Okay. Now, when is a system causal? Well, a system is causal if the output at time n does not depend on any future values of the input. Namely, y of n does not depend on x of n plus k for any positive values of k, for k greater than 0. Notice that I have k strictly greater than 0 here. Or equivalently, we can say y of n does not depend on x of n minus k for any negative values of k. Right? Now it's going to be easier to think of it in the second way, because what it means for this convolution sum is that if the result of this convolution sum should not contain any x of n minus k for negative values of k, what that means is h of k must be equal to 0 for all negative values of k. In this case, the linear time invariant system is causal. Okay, and this kind of makes intuitive sense Because if you look at the impulse response, what this means is that the impulse response has to be right-sided, or it has to begin at 0 and it can perhaps go on forever to infinity, but only for positive values of n. It has to be 0 for all negative values of n. Okay, and why does that make sense? That makes sense because we know that the impulse response is the response of the system to an input x of n, which is the impulse signal or the delta function. And we know that the input is non-zero only at time n is equal to 0, or you can think of it as an impulse that occurs at time n is equal to 0. Now, if a system is causal, this input can only affect the values of y of n for future, for values of n greater than 0, right? It should not, or any value of the output for negative values of time cannot be affected by x of 0. And since the impulse response is the response of the system to an unit impulse, it makes sense to say that an impulse input signal can only cause a right-sided signal as the output, or equivalently the impulse response has to be a right-sided signal. Okay.